Continuing our discussion of buffer overflows, I've already loaded our program into Immunity, and I've set a buffer near the start of my main function where I'm copying the string main function into my variable location. I'm going to go ahead and run to that location, and we're going to see what happens with our program. So a couple of things that you'll notice over here, our registers are set with a couple of values. What is the stack doing over here? There's a return to a Microsoft C call that's on the stack. And then down here, you see there's some other information. So let's go ahead and we'll step through this and we'll see how this changes as we go through each step. So right now, I'm going to make a change. And you see right here what happened. I just set this equal to the memory location where main function is stored. And that's memory location 403011. So if I were to have a look at that memory location, I should see that string is stored there. So it's just past the end of my memory dump, but we can see that that's the value that it contains. If I step again, I will see that this value, 1122344, has been stored here. These are the local variables being stored on the stack. Now I'm going to add 4 to this value here in EAX, and I'm going to move some information. So when I call this method, I am moving a value here, and here it is. I have a string of a bunch of A's that I've passed. Now remember, if I want to set parameters for my debugger, I can do so by selecting debug and arguments. And here are the arguments I'm passing, just a string of A's. So I'm getting ready to call this function. So this is sort of the preamble for calling this particular function. And now I'm going to move my data, step again, and that data has now been moved here on my stack again. So I have my data on the stack, and now I'm going to make my call. So notice the stack top is at 22FF50. This is going to change as soon as I make this call. So now what happened? I pushed the return address onto the top of the stack. This bumped down a line. And here I will push some more stuff. So when I trace this, I pushed EBP, and we said that's a frame pointer. And we have that here, 22FF78. That's the address here. That's saying this is the boundary for the buffer for this function and the last function. And now I'm going to subtract 38 from the stack pointer. That's going to change the size of my stack. So you will see that as soon as I step, boom, this just got bigger. So why is that? I'm making space for these local variables. So once again, I'm going to call this move method, and I'm going to move the string function onto my stack. So remember, here is the bottom of my current frame. And notice I put function here. And I'm going to move some other things onto the stack, some other local variables. So here I've moved more data onto the stack, and I do a couple of those calls. And now I'm preparing to call the stir copy function. So notice what's on my stack. Here's my source. I'm trying to copy this to the memory location 22FF20, which is here on my stack. I'm going to overwrite all of this information here. I step once again. I'm going to go ahead and step over. I'm right now in some library code. There's some optimizations in this library code, and it will move things in chunks. So as I step through this, notice what's happening over here. I get another batch of 41414141, which is A's. So again, you can see as I step through this, I will get some more A's, Now I'm going to overwrite a variable. Now I'm going to overwrite the function space, and I'm overwriting stuff like mad here. So I just keep going through. I probably got a little bit crazy with the A's, but that's all right. Hopefully I'll get out of this function soon. I'm tracing through this. Sometimes you can get a little bit overboard here and you try to give it too much information. So it surely will die. It just doesn't die in the exact way that you want. So I'm finally out of my function here. And now once I call leave and then return, the program's going to die. So I will go ahead and step. And sure enough, boom, the program has crashed. It says I can't read that address that corresponds to all of those A's. So in order to prove what we said earlier, I wrote a simple Python script that will exploit this vulnerability. So I first send out 44 A's, then I will send the return address, which we saw in immunity. So we can actually look in immunity and verify that it was 22FF44. If I go back to my script, that's what I have. Again, remember it's little endin. And then my shell code follows, which is something I got from Shellstorm. But there is a little bit of a problem here. The problem is this byte that has 0 in it. And this byte is interpreted as a null, and it truncates any kind of stir copy operation, etc. Now, we will talk in some future videos how to get around this, but you have to use a couple of tricks. When I run my script, it's going to be a little bit unhappy with me. So let's try this script, and I'm going to run it, go to my command prompt here, and I need to run Python, and I need to run it on exploit.py. As soon as I do that, it says, whoa, hold on now. You have null bytes in your strings, and I'm not happy about it. Now, just to show you that this is really in the right place, I'm going to replace the zeros with 1, 1. Save my script, and I'm going to rerun it. So here I am back at my command prompt. I will rerun this script. There was a problem, and notice the address. The address is offset 1122FF44. So this is exactly the value that I put in here, and this tells me that I'm in the right place. We will go into some details on how you can fix this in some future videos.